Hello everyone, I'm Sriram from NEC Labs America. This is a video about our paper Divide and Conquer for linear diverse trajectory prediction. Consider this scenario where cars are moving in the opposite directions. Implausible predictions of agents that interact with the SDB's route can make SDB take conservative actions. Moreover, predictions that do not follow road semantics can also lead to SDBs executing dangerous maneuvers. Similarly, in situations where a SDB is trying to take turns, the oncoming vehicle can either yield or accelerate. This requires SDB to have multimodal predictions that cover different modes of the distribution. Overall, having multimodal predictions with strong semantic coupling is crucial to have a reliable prediction system. Our work is divided into two parts. First, we focus on predicting multimodal outputs using multi-choice objectives, and then propose ALAN to obtain strong semantic coupling by imposing constraints on the driving behavior. Specifically, we focus on using multi-choice learning and propose a better initialization to winner-takes-all objective. Previous works. Vanilla objective depends on initialization for optimal convergence. Hence, this makes training process very brittle. Follow-up works such as RWTA solve the convergence problem by adding residual weight to the non-winners. And finally, EWTA was proposed to make training more stable, but all these works still suffer from the problem of outputs occupying spurious modes. We propose divide and conquer objective that acts as a better initialization to winner-takes-all loss. Consider this law example shown above. In the first stage, DAG penalizes all hypotheses with the entire data causing all predictions to go towards the center of the distribution. Then we divide these hypotheses into two sets, where the first set consists of initial half of the outputs and rest of the hypotheses go into the second set. We then backpropagate through a set of outputs which contain prediction closest with that of the ground truth. This leads to sets forming centroidal Voronoi tessellation at every stage. We perform this iteratively where every set after few thousand iterations is broken down into halves, leading to winner-takes-all objective in the end. We conduct experiments of DAG on a car pedestrian dataset that contains multimodal ground truths. We evaluate how well the multi-hypothesis prediction capture the true distribution of samples in the test set. We use evaluation metrics such as Oracle error and EMD distance and show that proposed DAG outperforms other variants of WTA. We now describe ALAN network that uses existing lane center lines as anchors. We utilize both rasterized top view information and lane center lines as input to our network. First, we feed the input through a set of path trajectory and center lane encoder to obtain a set of features for every lane and every agent. We concatenate these feature inputs and place them in the standard dimension at their corresponding location on the map. Along with the rasterized BEV, we pass it through a multi-agent convolutional encoder. We then extract hypercolumn descriptors of every agent. The intuition is to capture interactions at different scales where higher convolutional layers capture the global context while low-level feature retain the nearby interactions. Then the descriptors are fed through a set of MLPs, the hypercolumn trajectory decoder. As a primary outputs, we predict trajectories in normal tangential coordinates with respect to every input lane. Further, we make auxiliary prediction in global Cartesian coordinates of the map to regularize our anchor outputs, because two trajectories having same NT values can have completely different dynamics based on the input anchor. Our inverse optimal control module then outputs a score for these predictions by maximizing the reward based on their distance with the ground truth. We supervise our network based on three objectives. First is a winner-takes-all based reconstruction loss, which is initialized using our proposed DAG approach. Further, we regularize our primary and auxiliary predictions with each other. And finally, we have an IOC-based cross-entropy loss. Here are the video results from our work. As seen, ALAN shows multimodal predictions with tight semantic coupling. ALAN provides on par or better performance with other state-of-the-art methods from New Scenes benchmark. Moreover, it achieves significantly low off-road rate, indicating strong semantic alignment with the road. In conclusion, we propose DAG to learn better multimodal predictions and ALAN to impose constraints in driving behavior for trajectory prediction. We learn better multimodality in ALAN using DAG, while we obtain strong semantic alignment with the help of anchored lanes. Kindly refer to our paper for more details. Thank you.